Nowadays, large collections of images and 3D shapes are available online. Many times the objects are the same, but cannot be compared due to the different representations used for images and 3D models. Several approaches have successfully solved this problem by doing shape retrieval from images to be able to compare the both of them. Usually, this approach creates a common representation of images and 3D shapes. This is very limited as we cannot understand and compare the different parts that compose an object. We propose a new approach that can handle the shape of each part and combine parts from different sources to find a different 3D shape. Our approach automatically extracts the desired part and its 3D shape from each source. Using the part information, it then solves an optimization problem to find the 3D shape that best fits the arrangement of parts. Our approach builds a shape manifold per part using only the 3D models. To create the part manifolds, we extract the light field descriptors of each part. The light field descriptors are then used to build a manifold space for each of the parts using multi-dimensional scaling. If we look at the created manifold for one of the parts, we can see that objects that share the same part shape can be found close to each other. All objects are present in all manifolds, but the neighborhoods will be different depending on each of its parts. Once we have the shape manifold, we will train a CNN that will learn how to obtain shape manifold coordinates from an image. We use a single CNN to extract the shape of all parts from an image. Our deep learning architecture extracts the parts of an object by learning the semantic segmentation of each part. We present a novel architecture called ManifoldNet. The first stage of ManifoldNet extracts the segmentation of the parts of an object, while the second and third stages are specific for each of the different parts of an object and focus on learning how to map an image to the 3D shape manifolds. Imagine that we want to find a chair that contains the back of image number 1 and the legs of image number 2. We first extract the description of the shape of each part using ManifoldNet. Using each of the part descriptions, we then find the most similar 3D shape containing the parts that we have selected by solving an optimization problem. We show how our approach can handle many kinds of part shapes to find a matching 3D model. Our approach also understands if the object in the image does not have the selected part, and it will generate a result that does not contain that part. We call our approach pick and mix because it allows us to pick different parts and mix them to find what we want. Because the CNN learns a shape representation, parts from 3D shapes and images can be combined to obtain the desired shape. As seen in these examples, our approach can use any number of parts to find the desired 3D shape. Here we see an example of how understanding the parts separately can be used to extract the shape from objects that are partially occluded.